Okay, so let us continue our discussion next with this definition. The definition of two vectors in an inner product space being orthogonal. So let's see what that definition is. If U and V are two vectors in capital V, where it is of course understood that capital V is an inner product space, because we are only considering such spaces here in this section. It's not explicitly mentioned. For two such vectors, we say U is orthogonal to V if the inner product of U and V is equal to 0. That's just a simple condition. So this is the definition. Now an immediate consequence of this is that when U is orthogonal to V, then V is also orthogonal to U. Note that if U is orthogonal to V, then V is also orthogonal to U. Since the inner product of V and U, which by one of the rules, one of the axioms for inner products, is equal to the orthogonal complement of the inner product of U and V, must be 0, because this is 0. And because of this fact, we can just simply say that U and V are orthogonal to each other when any one of them is orthogonal to the other. So this proves that the relation of two vectors being orthogonal in an inner product space is a symmetric relation. Okay, now based on this notion of orthogonality, we next have the definition of a subset, which will now, after we define it, we will show that it actually is a subspace. Let W be a subset of V. The orthogonal complement of W denoted by this symbol W superscript the perpendicularity symbol is defined as this. W perpendicular is defined to be the set of those vectors x in V which become orthogonal to all the vectors in W. So this means that we have to consider those x in this that are orthogonal to not just some vectors in W, but orthogonal to everything in W, all the vectors in W. Now this next result, which is the first result of today, proves that, or rather it states that this is a subspace of V. So this is our lemma. Four, 3. This is a subspace of V. Okay. Now let me first prove this lemma. The proof is extremely straightforward, but still we have to go through it. We will consider two special cases for this W perpendicular by taking two special W's. Let us first see the proof. So the proof has two parts. The first part is often overlooked but is very important. You have to first of all make sure before you go for verifying the condition for a subspace that the set you are considering, the subset you are considering is a non-empty subset. Note that this is equal to 0 for all W belonging to W, and this is a fact that we have already seen when we started the section and when we defined inner products. After that definition itself, we saw that if we take the inner product of two vectors in an inner product space and one of them is 0, then the inner product value has to be 0. And this is regardless of what W is. You can in fact take any vector from V, this is going to be 0. Now this condition tells us what? That 0 belongs to W perpendicular, hence and so the subset we are considering is actually a non-empty subset. It has some vectors from V. Now we can verify the condition for a subspace. Now let A and B belong to W perpendicular, and we are also going to consider two scalars, alpha and beta, and you understand that these alpha and beta in general are complex numbers. Then for any W belonging to W, because these vectors are coming from W perpendicular, we have these things. This is equal to 0 and the inner product of B and W is also equal to 0. Hence, the inner product of alpha A plus beta B and W, which by one of the rules for one of the conditions for a function to be an inner product, is equal to this alpha times the inner product of A and W plus beta times the inner product of B and W. So it becomes 0 as well. Plus this. So what does this tell us? This tells us that alpha A plus beta B is also in W perpendicular. Thus, so this is a subspace of V. So that completes the proof. Now let me take two special cases for W, as I was saying just now. Note that if W is, let me first of all take the easy case. Let W be equal to V, the entire space, because that is also a subspace of V. Then W perpendicular equal to V perpendicular. Now if we just simply use the definition, it will be the set of all vectors in V such that X is we can continue to write W orthogonal to W for all W belonging to V, because now the subspace is V. So what can we say about such an X? Does this condition tell us something special about X? Note that among all the possibilities for small w, X itself is also a possibility. In other words, the inner product of X and X should also be 0. But that implies that X should itself be the 0 vector. That means that this set consists of only the 0 vector. You can clearly see why this is equal to this. So if your subspace is very large as you want, namely the entire space V, then its orthogonal complement is as small as it can possibly be, namely the smallest subspace, 0-dimensional subspace. Whereas if your W is this, if your W itself is the smallest subspace, then what is W perpendicular in this case? Again, by definition, it's the set of those vectors in V such that this is equal to 0. For all W belonging to W, that condition here is not needed, because now W has only 0 in it, the 0 vector, and this should be equal to 0. Now we already know that this is true for all vectors in V, for all X, which is what we have written here. It does not matter if we consider 0 here or 0 here, because if you change the order, then you just supply the inner product with a complex conjugate. So if one of them is 0, then the other is also 0. But then this tells us what? This tells us that in this case, the orthogonal complement becomes the entire space V. So this tells us that there is a kind of, what can I say, some relationship between these two spaces W and W orthogonal, that if one of them is large, then the other becomes small. So that something together they maintain something, and that maintenance can be understood once we prove that for a finite dimensional space V, actually V is the direct sum of W and its orthogonal complement. One part of this is of course proving that V is their sum. And the other part in showing this involves showing this. Now this one we can show right now, but for this one we will have to wait. Okay, it will come at the end of this section, and together these two will enable us to conclude that V is the direct sum of W and W orthogonal. This one we can show now, and we are going to do so now. That is, the only vector common to a subspace and its orthogonal complement is the 0 vector. Let X be a vector in the intersection of these two subspaces. Then X being a vector in the orthogonal complement should be orthogonal to all the vectors of W for all W belonging to W, but at the same time X itself is also in W. So in particular, if you take W equal to X, we should have this, but which implies that X should be equal to the 0 vector. Hence, this is equal to 0. You can write the singleton set 0, or you can write like this, which is the notation for the smallest subspace spanned by this subset. We have already come across that notion. Okay, so but that other fact that V is the sum of these two subspaces, that we will have to wait for some time. Now, instead of that, let us look at another notion, also dependent on the idea of orthogonality of vectors. Let Vi be a set of vectors in some inner product space V. Although in general we can just simply say let W be a set of vectors in an inner product space V, but because we will mostly be working with finite dimensional inner product spaces in which we will have to consider this type of sets that we are now defining, so that's why the author has chosen to write Vi. I think it's because of that. Anyway, this is just any subset of vectors in some inner product space V. We call the set Vi and orthonormal set of vectors if the following two conditions are satisfied. One of those two conditions is orthogonality, the other one is normality, and that normality condition demands that all the vectors in this set be of length 1. Each vector Vi is of length 1, which is equivalent to demanding that the inner product of each Vi with itself is equal to 1. Length is just the square root, non-negative square root of this, so that is 1 if and only if this is 1. And the second condition is orthogonality. For I not equal to j, which ultimately means considering two distinct vectors from this set, the corresponding vectors Vi and Vj are orthogonal to each other. Now, this type of sets are very important in inner product spaces, and in finite dimensional inner product spaces, whatever that space is, each such space turns out to have one such set as a basis. Okay, we will go to that result, maybe not today, but let us now see some consequences of orthonormality. In this next lemma, we see the first thing. Lemma 444. If Vi is an orthonormal set if this looks somewhat strange to you, you can just simply take a set of vectors W here, that's it. Because these conditions would still remain meaningful. If Vi is an orthonormal set, then the vectors in Vi are linearly independent. Any orthonormal set is automatically linearly independent. Then the vectors in Vi are linearly independent. Also, if you consider a vector like this, say W, which is a linear combination of some of these Vi's, say alpha 1 V1 plus alpha 2 V2 and so on, plus alpha n Vn, where n is some positive integer, then the inner product of W with Vi is equal to the ith coefficient in this linear combination, that is alpha I, for all the I values. Okay, so let us now see the proof. These are just some technical facts. The proofs are not twisted or difficult at all. Almost all of them are extremely straightforward, but the facts are important. Okay, so the proof goes like this. Let us consider some scalars, some complex numbers, for which this linear combination is equal to 0. So you understand that we are trying to prove that the given set is linearly independent. Having assumed this, now we have to show that each beta I is 0. If we can show that, then the set will become linearly independent. So what we are now going to do, we are now going to consider the inner product of this. This is after all a vector, right? Being a linear combination, it's a vector in the inner product space. We are going to consider the inner product of this vector with all the vi's, taking one vi at a time, of course. Then for any integer, let me call it j, lying between 1 and m, you watch these steps. 0 is equal to this, definitely Vj is some V coming from this set, and this 0 is the 0 vector, this 0 is the complex number 0. Now in place of this 0 vector, we write this linear combination. Beta 1 V1 plus beta 2 V2 plus beta m Vm comma Vj. Now using the one of the axioms for an inner product, this becomes beta 1 times the inner product of V1 and Vj plus beta 2 times the inner product of V2 and Vj, plus if we continue like this, then there is a term where we have Vj itself in this linear combination. So that is beta j times Vj comma Vj, and the last one is beta m times Vm comma Vj. Now we use the fact that these Vj's these Vi's are all coming from an orthonormal set. So among all these inner products that you see in this combination, precisely this is 1 due to normality, and the other inner products are 0 due to orthogonality. This being 1, that comes from condition 1, and the others being 0, that comes from condition 2. So that leaves us with what? Only beta j. So we have ended up proving that beta j is equal to 0. But this we have done for any j. So that means all these beta j's are 0. Thus, beta 1, beta 2, all of these things are 0. Hence, our set of vectors is linearly independent. Let me write like that, linearly independent. But we have something else also to prove, which also follows almost from this calculation itself. Also, so we just straight away calculate the inner product of, is it Vi? What is the exact statement? Yeah, it is Vi. We just straight away calculate this inner product. So we know what W is, it's already given. alpha 1 V1 plus alpha 2 V2 plus alpha n Vn Vj. Here I deliberately took n just to differentiate it from this given one. So some term alpha j will be there, alpha j will be there in some term, and there we will have Vj comma Vj plus alpha n Vn comma Vj. And you can see that just like that calculation, this is going to be equal to alpha j. There we had a condition that these things become equal to this complex number 0. Here, however, we do not have a condition. We just have this, and that's what we wanted to prove. So you can see what we have proved in this lemma actually. In an inner product space, if you have an orthonormal set, then you know that it's linearly independent. That is one half of this result. And the other half says that if you have a vector that is a linear combination of some of these vectors from this orthonormal set, then the coefficients are given by inner product. That means the coefficients are all inner product values. Okay. So now there is something going on outside, a religious some gathering is there, because of which it's becoming very difficult to film. So I think I'm not sure whether you can hear it, but it's really loud. So I think it will be better if we stop it here, because anyway I was going to just simply prove one more result. But let me just stop here itself, because I don't know how louder it's going to get after this. So sorry for this inconvenience. And on top of that, I'm not really quite feeling well. I was not well recently, and I have not fully recovered. So because of that, I have to stop the video here itself. The next upload is this coming Friday, and on Friday let us go through calculus. So with that, I bid adieu for tonight. So see you on Friday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.